Hello, good morning. Today we're going to talk about Chapter 5. We're going to start talking about Chapter 5, which is entitled Exponents and Polynomials. And in particular, today we're going to start with the first section of Chapter 5 entitled Exponents. Alright, of course, we all know what exponents are all about from our first course in algebra. As a brief review, if I've got 2 raised to the third power, well, 2 we refer to as the base. 3 is, of course, the exponent. And it's really just a shorthand for extended multiplication. 2 to the third power is nothing more than 3 factors of 2, and 2 times 2 times 2 is, of course, 8. Talking about variables, if I've got x to the fifth power, all that is a shorthand expression for 5 factors of x, where of course a factor is an element of a product. And if more generally I've got y to the nth power, well, that means I've got y times y times y. I've got a string of n factors of y all being multiplied together. Alright, our book is talks about a bunch of rules for exponents, rather extensive list. So let's get right to it. Rules for exponents. Now the book doesn't number these rules, but it does name them, so I'll give the same names for these rules that our book gives. The first rule they talk about in this regard is a product rule for exponents. Now I'm sure some of these rules, maybe most of these rules, will be familiar to you, so let me briefly get right at it. If I've got x to the mth power times x to the nth power, well, basically I'm multiplying factors with the same base to perhaps different exponents. I keep the same base and add the exponents. So x to the mth times x to the nth is x to the m plus nth. That's our product rule for exponents. As a simple example, if I've got x to the 11th power times x to the 5th power, well, that's nothing more than x to the 11th plus 5th power. So it turns into really an arithmetic problem at the exponent level, and that's, of course, x to the 16th power. All right. Another example, if I've got y to the 4th power times y to the 5th power times y, well, don't forget, when there is no exponent explicitly stated, we assume an exponent of 1. Let me write that out. So this is really equivalent to the y to the 4th times y to the 5th times y to the 1st power. Y to the 1st power means 1 factor of y. And of course, to simplify this expression, I'll just add those exponents at the exponent level, and 5 plus 4 plus 1 is, of course, y to the 10th power. So a simplification there. Let's try another one. I'm going to be doing lots of examples today in this lecture. Let's say I've got a squared times b cubed times a cubed times b squared. Alright, when exponent expressions are sitting next to each other like this, there's really implied multiplication going on. And as we all know, multiplication is commutative. Multiplication is associative. That means I can multiply these factors in any order I like. And there should be a 2 there. So of course I'm going to group the powers of a together. I can crunch those together, and I'm going to group the powers of b together. B cubed times b squared. Of course, a squared times a cubed is a to the 5th power by our product rule for exponents, and b cubed times b squared is, of course, b to the 5th power. And we would probably write our answer in implied multiplication type fashion, namely a to the 5th times b to the 5th. Another example, minus 8 times x to the 4th power times x cubed. Alright, Again, these are implied multiplications going on there. I can put dots in there to make the multiplication explicit. And I'm going to crunch together these powers of x, of course. X to the fourth times x cubed is x to the seventh. Keep the same base and add the exponents. Minus 8x to the seventh. Alright, so that's our product rule for exponents. Next I want to talk about is our power rule for exponents. The book calls this rule power rule for exponents. And to state the rule simply, if I've got x to the nth power, in turn raised to the nth power, some books call this a power of a power expression, all I do is multiply the exponents. So x to the nth raised to the nth power is x to the m times nth power. Some examples of this power rule for exponents would look like this. If I've got 3 squared cubed, well, invoking that rule, it's 3 to the 2 times 3 power. 3 times 2 is 6, so I've got a 6 exponent working on a 3 base, and 3 to the 6th power is, of course, 729. Let's deal with some variables now. If I've got x squared times x cubed raised to the 6th power, well, I suppose I would simplify first within the parentheses. X squared times x cubed is x to the 5th power by our product rule for exponents. So I really got x to the 5th power raised to the 6th power, and now I'll invoke my power rule for exponents and multiply those exponents, and I get x to the 30th power as a final answer for that example. Another example, x squared to the 4th power times x cubed squared. Alright, so I've got a lot of powers of x flying around here. Notice that's a multiplication, and I'm going to invoke my hierarchy here. I'm going to evaluate this first, then this, then multiply the result. Exponents first before multiplication, right? So the first circle, x squared to the 4th power, by my power rule, that's x to the 8th power, times x squared cubed is x to the 6th power, or x cubed squared, I should have said. X cubed squared is x to the 6th power. So now I'm multiplying 2 powers of x together, and I'll invoke my product rule for exponents. X to the 8th times x to the 6th is x to the 8th plus 6th, and of course that's x to the 14th power. Alright, so we've got 2 rules down, the product rule for exponents and the power rule for exponents. Now I want to invoke a new rule. I'm going to define a new rule. This is a power, the book refers to this as a power rule. I'm sorry, that was the previous rule. Powers of products and quotients. Let me write that down. Powers of products and quotients. So really our third rule today. Really this is 2 rules in one. Alright, a simple statement of the power of products, xy to the nth power. Basically I can distribute an exponent over a product, and our power rule for quotients is somewhat similar. If I've got a quotient to a power, I can distribute an exponent over a quotient. Alright, let's do examples of each of these. Let's say I've got x squared times y in parentheses raised to the 3rd power. Alright, by my power of product rule, I can take my exponent and distribute it over a product and multiply the result. So I can rewrite this as x squared cubed times y cubed. And now my power of a power rule, or power rule for exponents, tells me x squared cubed is going to be x to the 6th power, multiplying those exponents. And of course y to the 3rd power is just y cubed. So my final answer here would be x to the 6th power times y cubed. Alright, somewhat similarly, invoking this same rule over a quotient, if I've got x over y squared raised to the 4th power, again the rule above says if I've got a quotient raised to a power, I can distribute that power over each factor of that quotient. So I'll get x to the 4th power is x to the 4th power, and downstairs y squared to the 4th power, let me write that out, y squared to the 4th power. And of course I can simplify that a bit further, x to the 4th power in the numerator, and downstairs y squared to the 4th power is y to the 8th power. And that'll be my final answer for that example. Alright, let's do some more examples of this powers of products and quotients. Oh, need a zoom screen. Let's say this example, and you'll see in homework and on test day the instructions are simplify the following exponent expression. If I've got 2y to the 4th raised to the 5th power, of course if I've got a product in the parentheses and an exponent working on that product, I can really distribute that exponent over each factor of that product. So I'll take 2 to the 5th power times then y to the 4th to the 5th power. 2 to the 5th power is of course 32. 2 times 2 times 2 times 2 times 2 times y to the 4th to the 5th power. Well, the power of a power, you multiply the exponents, y to the 20th power, and my final answer would be 32 times y to the 20th power. One more example with a quotient. Let's simplify. Six x cubed divided by 5y to the 4th, all that raised to the 2nd power. Well, really I've got 4 factors involved in this product and quotient, and what I can do is invoke 2 rules at once and really distribute this outer exponent over all 4 of those factors. Alright, so 6 squared is 6 squared. X cubed squared is x to the 6th power. Downstairs 5 squared is 25. I'll write it as 5 squared for now. And y to the 4th squared is y to the 8th power. Alright, so of course I can evaluate this more precisely. 36x to the 6th power divided by 5 squared is 25 y to the 8th power. So that kind of tells it all regarding that powers of products and quotients rule. Next thing I want to talk about is 0 exponents. Alright, well, as you probably know, anything to the 0 power is 1. No matter how simple, no matter how complicated, anything to the 0 power is by definition equal to 1. If I give some simple examples here, well, 3 to the 0 power is 1, of course. Minus 7 to the 0 power, well, of course, that also equals 1. Let's get something a little more complicated here. 3x squared times y cubed, in turn raised to the 0 power, equals 1. Anything, no matter how simple, no matter how complicated, if it's raised to the 0 power, it's equal to 1. Let's look at something that looks like this. Example, 5 times x to the 0 power. The book makes a big deal out of this type of problem. That 0 exponent is only working on this variable x. Notice, that's an implied multiplication here. So if I see 5 times x to the 0 power, really, there's an invisible set of parentheses isolating that exponent operation first. Remember, exponents first, multiplication later. So anything to the 0 power is 1. So 5 times x to the 0 power is 5 times 1. And 5 times 1 is, of course, 5. All right, I've got no problem on test A if you skip all this formality and run right to the final answer. Let's try something else. Minus 5 times CD to the 0th power. All right, this may throw some students. Notice if this negative sign is floating outside, well, notice it's outside of this exponent process. The base of that 0 exponent is 5CD, so you have to evaluate that first. Well, anything to the 0 power is 1. So minus 1 times 1 is, of course, negative 1 for a final return. And if I've got a string of factors, something like this, 5 times 8 to the 0 power times b, well, again, these are products, and a to the 0 is 1, so this is really 5 times 1 times b, which, of course, returns a 5b. All right, next topic I want to talk about is negative exponents. And there's really two rules for negative exponents. To be applied here. And let me write them both down. X to the minus nth power, by definition, is 1 over x to the nth power. So let me put a big circle around this. This is important, so I can work out some simple examples here. 3 to the minus 2 power. All right, you'll hear me say this expression quite a bit from here on. I'll give this acronym: simplify and express with positive exponents only, so I don't have to keep writing that over and over. SAUPIO, I guess you call it. Simplify and express with positive exponents only. Basically, the author is giving all their answers and asking for all their answers with positive exponents only. Alright, so if I ask you to simplify 3 to the minus 2 power, well, by definition, by this rule right up here, 3 to the minus 2 is 1 over 3 squared. Basically, move your factor down to the denominator and change the exponent sign. And 1 over 3 squared is, of course, 1/9. Let's try again. Simplify and express with positive exponents only. Minus 2 raised to the minus 5th power. Now, we tend to get all kinds of crazy answers for problems of this type, but it's not really that difficult if you remember the rule. All right. Minus 2 to the minus 5th power is nothing more than 1 over minus 2 to the 5th power. Notice the base sign does not change, but the exponent sign does. I move that expression down to the denominator as a factor. It's 1 over minus 2 to the 5th power. Alright, well, what is minus 2 to the 5th power? Minus 2 to the 5th power is, it's 5 factors of minus 2. All right, and anytime you've got a odd string of negative factors, you're going to get a negative return. And 2 to the 5th power is, of course, 32. So your final answer for this expression, simplifying this expression, is 1 over negative 32, or our author would probably absorb that negative sign in the numerator. Either of those answers are fine. Alright, more on negative exponents. How about something like this? Simplify and express with positive exponents only. 7m to the minus 8th power. Well, notice that's an implied multiplication between the 7 and the m to the minus 8th power, and we need to deal with this exponent first before we multiply. M to the minus 8th power is 1 over m to the 8th power by definition. And now I'll just multiply across. 7 times 1 is 7, and I get 7 over m to the 8th power. That's a completely simplified answer with positive exponents only. Let's try another one. Simplify and express with positive exponents only. And problems like this tend to confuse students and instructors sometimes. Well, let's take it a step at a time. I've got negative c to the minus 2 power. Well, please note that this negative sign is not involved in this exponent operation. I can really rewrite this expression as negative 1 times c to the minus 2 power. Alright, now I'll clear up that negative exponent. I'll get minus 1 times, well, c to the minus 2 is 1 over c squared. And now multiplying across, I'll get negative 1 in my numerator and positive c to the positive 2 in the denominator. Let me rewrite that. Final answer, minus 1 over c to the positive 2 power. Okay. Still more on negative exponents. Simplify and express with positive exponents only. Let's say we've got x to the minus 5th power times x cubed. Well, we know from the very first rule we talked about today, the power rule, product rule for exponents. Product rule for exponents. That was the name of the first rule today. All that says is if you're multiplying exponent expressions with the same base, you keep the same base and add the exponents. So all these rules that we've talked about previously today, they all hold for negative exponents as well. So x to the minus 5 plus 3 will give me a negative 2 in my exponent, and x to the minus 2 power is, of course, 1 over x squared. Notice we want our final answer to have positive exponents only. Try another one. Simplify and express with positive exponents only. Let's say I've got x to the minus 5th power raised to the minus 3 power. Well, you may recall our power of a power rule. When you take a power expression and raise it to another power, you equivalently can keep that same base and multiply the exponents. All right, so minus 5 times minus 3 at the exponent level is positive 15. So that would be a good result with positive exponents only for that expression. Alright, so again, we're still talking about negative exponents. And we've covered this first rule for negative exponents. X to the minus n is 1 over x to the n. Well, what about if you've got an expression that looks like this? 1 over x to the minus nth power. Well, it turns out in this denominator, x to the minus nth power is 1 over x to the nth power, is it not? These expressions in the parentheses and the denominators are equivalent. And of course, when you divide by a fraction, you can equivalently invert and multiply by the numerator. And 1 times x to the nth over 1 is x to the nth power. So what I've just done is derived a second rule for exponents. Let me put this in pink, because I'm going to add to that another rule, this second rule, that says, well, if you've got a negative exponent in your denominator, you can move it up to your numerator by changing the sign of the exponent. Okay? So there's our two rules for negative exponents. X to the minus n is 1 over x to the n, and 1 over x to the minus n is x to the nth power. Alright, fresh screen. Alright, note. Invoking both of those negative exponent rules at once, I can easily simplify something like this. By our first rule for negative exponents, so it says I can move this factor down to the denominator and say it's 1 over x to the mth power. And by our second rule for negative exponents, I can move this upstairs and call that x to the nth power. Can we not? And we can use both of these negative exponent rules in tandem to simplify some nasty expressions. Simplify and express with positive exponents only. For example, 1 over c to the minus 10th power. Well, the second rule for negative exponents says, well, if I've got a negative exponent expression in my denominator, I can move it upstairs to my numerator and change the sign of the exponent. So 1 over c to the minus 10th is c to the 10th power. And another, simplify and express with positive exponents only. 5 to the minus 2 power over 4 to the minus 3 power. Alright, very simply I can invoke our negative exponent rules. I can shift from numerator to denominator as long as I change my exponent signs. And the goal here is positive exponents. So 4 to the minus 3 power downstairs comes upstairs as 4 cubed. Similarly, 5 to the minus 2 power upstairs comes downstairs as 5 squared. All my exponents are positive now, so I can easily evaluate. 4 cubed is 64, of course, and 5 squared is 25. So this would be my final return, 64/25. Simplify and express with positive exponents only. This one's a little nastier. 6h to the minus 6th power over 8r to the minus 7th power. Alright, and I'm not sure how formal you want to be here. Well, if I look at this negative sign, that really means a multiple of minus 1 in my numerator. And downstairs, 8 times r to the minus 7th, I'll write it just like that, 8 times r to the minus 7th. Right, the minus 1 and the 8 have to stay where they are. What I can do is move the h to the minus 6 to the denominator as h to the 6th, and move this r to the minus 7th to the numerator as r to the positive 7th. Now don't forget about those factors of minus 1 and 8 in the numerator and denominator respectively, right? Alright, so I've got minus 1 times r to the 7th over 8h to the 6th, and multiplying by 1 is redundant, so I think our author would give the answer as minus r to the 7th divided by 8h to the 6th. You've completely simplified and equivalently expressed with positive exponents only. Alright, next rule our book talks about is they talk about a quotient rule for exponents. And really it's an extension of the first rule we talked about today. Well, you might expect if you multiply the same bases, you can add the exponents, keep the same base, and add the exponents, and somewhat similarly for quotients. If you're dividing the same base expressions, you keep the same base and subtract the exponents. So there's another important rule. Example: a to the fifth over a cubed. Well, according to this above rule, it's a to the fifth minus 3 power, and of course that reduces to a simple a squared. Now, of course, I could have worked this out with a little more ink if I need to. In the numerator, a to the fifth is 5 factors of a, and the denominator, a cubed, is 3 factors of a, and of course 3 factors of a in the denominator cancel out all but 2 factors of a in the numerator, and I get the same answer thinking about it perhaps a little more informally. So a to the fifth over a cubed is a squared. Let's try something a little more interesting. Simplify. 3 times b to the minus 3 power divided by b cubed. Now again, that 3 times operation is isolated from the exponent operation, so what I'm going to do is rewrite it like this. In other words, the 3 has to stay in the numerator. And b to the minus 3 power can come downstairs as b cubed, can it not? So I've got 3 divided by b cubed times b cubed. And of course, when I multiply the same base expressions, I keep the same base and add the exponents. So my final return for this problem would be 3 divided by b to the 6th power. Alright, let's build up our muscles here a little bit, try to tackle some things of increasing complexity where these rules are layered one upon the other. Again, the goal here in these problems is to simplify as much as you can, and your answer must contain positive exponents only. That's what the PEO stands for, positive exponents only. X to the fourth times x cubed divided by x to the minus fifth. Alright, now there may be one way to go about this. I'd like to try to spend the least amount of ink as possible. X to the fourth times x cubed in the numerator, that's going to be x to the seventh, divided by x to the minus fifth in my denominator. Of course, what I can do now is move this x to the minus fifth upstairs as x to the positive fifth divided by 1. Right, when I move everything else gone, our invisible 1 appears in my denominator. Of course, dividing by 1 is redundant, so I'll get x to the 7th times x to the 5th, and that's x to the 12th as a completely simplified answer with positive exponents only. Let's try another one. Simplify and express with positive exponents only. X squared times y cubed divided by 7 xy to the fourth. Well, let's see. I'm going to try to go about this a little less formally than our author does. All right, I know that 7 doesn't have any exponent working on it, so it's got to stay where it is. What I'm going to do is crunch together the powers of x. And I know that x squared divided by x, well, I suppose I could call it x to the 2 minus 1. I'm going to say the 1x in the denominator cancels out all but 1x in the numerator. So x squared over x reduces to x in the numerator. And of course, y cubed over y to the 4th, well, 3 factors of y in the numerator cancels out all but 1y in the denominator. So I think informally, with the least amount of ink possible, this really turns into a one-step problem. Final answer, x over 7y. Alright, this one's a little nastier coming up here, so let me get some room here. And this more or less represents the upper limit of difficulty in this section. Simplify and express with positive exponents only. 2a to the minus 2 times b cubed over 3a to the 5th b to the 4th. And that entire mess raised to the 3rd power. So I want to end up with a completely simplified answer with positive exponents only. Alright, what I'm going to do is simplify within the parentheses as much as I can before I go on. I notice I can bring down a to the minus 2 power as a squared in my denominator. Can I not? As long as I change the sign. Let me do that here. A to the minus 2 power comes downstairs as a squared, joins up with a to the 5th, and I'll have 7 factors of a in my denominator. Similarly, well, somewhat similarly, I can crunch these powers of b together before I go on. 3 factors of b in the numerator, 4 factors of b in the denominator. I'll have 1 residue factor of b left in my denominator. Looks better already. The 2 and the 3 have no exponents working on them, at least not internally, not inside the parentheses, so they have to stay where they are. So notice I've simplified as much as I can within the parentheses. Now I know from my rule for products and quotients that I can distribute my exponent, my outer exponent, on all 4 of these factors and multiply or divide the indicated result. Alright, 2 cubed is 8 in the numerator, divided by 3 cubed is 27 in the denominator. A to the 7th cubed, well, power of a power, you multiply the exponents. And similarly, b cubed in the numerator and the denominator turns into just b cubed, right? Alright, so I think we've completed that with as little ink and as little effort as possible. 8 over 27 a to the 21st b cubed. Alright, let me get a fresh screen here. And there's one last rule that our book talks about that will make the homework problems a little easier, some of the more complicated ones. So bear with me here, I know it's a long section. Quotients raised to negative powers. Well, let me give you the rule first and then we'll work some examples out. If I've got a quotient raised to a negative power, well, what I can do is distribute that negative exponent over both factors of that quotient. And as before, if I've got a negative exponent in my numerator, I can move it downstairs as a factor with a positive exponent, and similarly If I've got a negative exponent in my denominator, I can move it upstairs as a positive exponent factor. And notice I can rewrite this expression as y over x, so it should be an x there, y over x raised to the nth power. What I've just done is proved this quotient raised to a negative power rule. Basically, it says this. If you've got a quotient raised to a negative power, I can invert that internal fraction and change my exponent sign to a positive. And that may be very helpful for some nasty problems. Let me give you some examples of how to use this. Simplify and express with positive exponents only. Let's say I've got a fraction 2/3 to the minus 4 power. Now I could waste a lot of ink here, or I could invoke my rule above and say, well, I could just say this is equivalent to 3/2 to the positive 4th power, and that looks a lot better. And I know that 3 to the 4th power is 81 in my numerator, and 2 to the 4th power is, of course, 16 in the denominator. So that would be my final return. Really a one-step or maybe two-step problem if you invoke this rule. Let's try another one. Simplify and express with positive exponents only. Well, let's work with some variables here. If I've got y squared over x cubed to the minus 3 power, alright, the above rule says if you've got a quotient raised to a negative power, I can invert that quotient and change the outer negative power to positive. Makes it quite a bit quicker. Alright, so in my numerator, x cubed is of course x to the 9th, multiplying those exponents, and downstairs y squared cubed is y to the 6th. Again, kind of a nasty problem turned into a one or two stepper if you can apply the rule properly. One more example for the day. Simplify and express with positive exponents only. And this one's a little nasty, but as you'll see, we can kind of tame things a little bit if we play our cards right. A to the minus 2 times b cubed over a squared a cubed b to the 4th, that entire mess raised to the minus 3 power. Alright, what I'm going to do is, well, I see I've got a quotient here raised to a negative power. What I'm going to do is invert this quotient. I'm not going to change the sign of any of the exponents inside, and change that outer exponent to a positive 3. So all I do here is swap numerator for denominator and vice versa. A squared a cubed b to the 4th over a to the minus 2 b cubed. Notice I haven't changed anything inside, or the signs of any exponents inside. I've just changed the outer exponent from a minus 3 to a positive 3, and I claim it looks better already. Alright, let me simplify as much as I can inside my parentheses now. A squared times a cubed is a to the 5th, and of course I'm going to bring this upstairs as a squared, and that'll get me 7 factors of a in my numerator. Notice, I can similarly crunch these powers of b together. B to the fourth over b cubed. That will leave me one factor of b in my denominator. And when you cancel everything out in your denominator, a redundant divisor of 1 appears. Of course, I'm not going to show a divisor of 1 in my final answer. And now this turns into one of the easier problems earlier today. A to the 7th cubed is a to the 21st power times b cubed is just b cubed. So there's my final return, completely simplified with positive exponents only. Alright, this pretty much represents the upper limit of difficulty in this section, so we'll call it a day. One thing I do want to mention, we did talk about a lot of rules today. Depending how you count them, there's 9 or 10 exponent rules. So I'm going to ask you to see page 405 for a nice table summary of exponent rules. And as you work out your homework problems, you might want to consult the table, summary table of exponent rules. Alright, we're hitting the 46-minute point, so we'll call it a day for this section 5.1, Exponents.